Hello guys, today we're going to be learning about the AWS Certified Solutions Architect exam. This is supposed to prepare you and just kind of break down what each service does and why we even need services. Let's go ahead and just start. Okay, so the first category we have to learn for AWS is actually why the compute power. So what is computation? What is computing, right? So let's see. When AWS says compute, it means where does your application actually run? That's a whole category. So in order to compute something, we actually have to use something called a server, right? And a server is just a compute whose job is to provide something to other computers. So basically think of a server kind of like an online computer. So I would say server, oops. I would say a server is kind of like an online oop. Let's erase this. Okay, so I would say a server. See, so a server is kind of like an online application, so online computer. So I would say server is like an online computer. It's kind of like a human, right? Okay, see, like a web server could give you web pages. A database server can give you kind of just a server that stores data. An application server runs your business logic, so it's kind of like just code that tells you if this happens, then you go ahead and run that. A file server is stores files, so I would say it's similar to a database server. Let's see, so your laptop is also a computer, but is mainly for you. A server is a complete built or configured to serve requests, such as user apps and other systems. So we could see that a restaurant analogy is that a customer makes a request saying, I want a burger, right? So we could see this as a kind of like a application server, and the kitchen receives the request and prepares the food as a result. The server is computing like a kitchen. Let's go erase all of this. Next is Next is, you guys might ask, why do applications need compute? Well, think about it. If we have just like a bunch of code, think about it. If we have code and then we have all of this, what actually runs all of this, right? For example, if I have like a bunch of tools, say tools in the toolbox, right? These are basically just tools, right? And materials. What do we use to run? If we have a bunch of tools and materials, we can't actually do anything, right? What can we do with this? Nothing much, right? So think of a server or computing power. Can be like a human. It's like a human which just works. Uses the tools. So it uses these tools and it just works to get stuff done. For example, how are we supposed to show a website if we just have code? We need something to host it, something to process the logins, something to order details. So we go ahead and just get information. We go ahead and put it into a server, and this provides a service, right? Just like how compute is like just info, humans are like a server, and work is like that service that just the humans can provide. This whole thing is computing, actually. Right, let's see. That something is compute. So AWS gives you multiple ways to run that computation depending on how much control you want. And we're actually going to teach you about all that control that's needed. So this exam basically ask you or teaches you what's the best way to run that workload. There's different things such as EC2s or like the Lambda service, but we're going to go ahead and just explain that to you later on. Let's see the 4 core ideas that you need to actually understand all of this. So we know that EC2 is a virtual server which you manage. So think of an EC2 as like a server. So EC2 is like just raw, just like think of it like a raw compute power. Maybe like an online computer. This is also known as a virtual computer. So like online computer. So auto scaling and load balancing is kind of so basically this is like a customer. Let's call it client. We like to call them clients. Makes a request, right? They do a request. That's a request. This means request right here. Okay, so the request goes to something called a load balancer. I'm just gonna say load balancer, and that kind of distributes to your servers. We're gonna have multiple servers running because we have horizontal scaling. So you could see these as servers, right? So as a client, there could be many clients. Let's say like we have like 1 million, right? That's why we have load balancers. So when we have 1 million requests, if we just give 1 million requests to one server, that server would actually just get overloaded and get canceled because it can't handle that many requests. Or it'll just take very long to load. That's why we have that. Yeah, this is why load balancers are very important. Well, okay, Lambda is something where you don't have to figure out all of this. So this is if you have an EC2, you would have to have a load balancer, configure how many servers you want, and just run all of this. But Lambda, we could just run code without managing any of these servers, and Amazon just does that for you. Next, we'll learn about ECS and Fargate, which is kind of how we could package apps cleanly and with less operations. All right, let's go ahead and jump into the first topic, EC2. This is just a brief overview right here. Okay, so EC2 is a virtual server in AWS. So virtual server is also standing for, so EC2 actually just stands for Elastic Compute Cloud. Okay, so E stands for elastic, C stands for compute. I don't know why there's a 2. Maybe the 2 means there's 2 C's, complete cloud, so it could also be known as ECC, I guess. Compute cloud. That's funny. Okay, so AWS gives you a computer in the cloud. So a computer in the cloud is also known as a virtual machine. I think I said virtual computer earlier, but it just means virtual machine. So basically Amazon has one huge computer, right? And instead of just running one function on this computer, we split it into millions of smaller computers, right? So let's say this has like a million computers. You could also do this thing with your own computer too by downloading something like Ubuntu. Yeah, but you would have to have a strong computer just so you could split it into many virtual computers or virtual machines. So, what does virtual mean? See, AWS has a huge physical machine in data centers. That's that big one right there. So they divide into multiple small ones, as I explained. And one of those virtual machines. So you have a very small little piece of this big server, and this would be called your EC2, which stands for Elastic Compute Cloud. But this thing though is just an online virtual. It's just a virtual machine from Amazon's big server because they just have such a big server. Okay. Let's see what what you choose with EC2. So EC2 gives you a lot of control actually, because it's not serverless. You pick the server, so you get to pick things such as how much CPU you want, how much RAM you want, the operating system like Windows versus Linux, what storage, what kind of like that'd be like MongoDB or Postgres, what network settings such as like private or public. Yeah, all right. See, why do we want EC2? Well, EC2 will give you full control. So let's say, what is full control? Well, full control is whatever we mentioned up here, such as RAM, compute speed, all of that. Yeah. So why would we need full control? Let's say it needs a special operating system configuration. It needs custom software installed. It's old and it's not easy to redesign, or always needs background processes running. It cannot fit into a serverless model easily. So I guess EC2 is kind of like the old-fashioned way of doing something, because now we prefer Lambda. See, for EC2, we're responsible for a lot of stuff. We have to manage patching the operating system, installing the software, scaling the number of instances. So we would have to have our own load balancer and choosing instance size. Renting at EC2 is like renting an empty apartment. It's I guess it's like an analogy to make you guys understand more. So think of EC2 like renting an apartment. We still have to clean it. We have to clean it. We have to, I guess, put some furniture, decorate ourselves, maintain. Basically, we have to maintain it. We have to maintain it ourselves. So we could customize as much as we want. Let's say we want like a TV right here. Say this is like a house. You want like a TV right here. You want a couch right here. There is no template, you know what I mean? So you go ahead and just do whatever you want. You could put a TV or eat breakfast in bed, like, okay, whatever the heck you want. You could spill something on the floor and just leave it there if you want. So you get a lot of power with EC2. It doesn't mean that it's easier. It just means that you have a lot more control. So you get to be your own architecture or your own architect. See, it's good when you need full control of the machine. It's not custom. Yeah, we went over that. So specifically for the exam, we have to figure out like keywords. So these are kind of like keywords for how you could tell if an EC2 is the answer. So we could see an app requires a custom driver. Custom is kind of like, okay, so they do it themselves. A company must control the operating system. Yep, that's like another custom thing. A software only runs on a specific Linux setup. Right, so this specific setup is not public, I guess. It's not public. Not public. Right, so that we're not used to it. So only your EC2 is familiar. So think of EC2 like a custom service. And a legacy app, yeah, with minimal code changes. Yep, these often point to EC2. Okay, now that we understand EC2 and how it's like a custom service, let's go ahead and move on to different types of EC2. Okay, so let's see. There's one where it's on demand. So if you use, for example, if you use 100 hours, you go ahead and just pay for 100 hours, right? Pay as you use. That's what on demand stands for, right? Pay as you go. So it's good for short term when things are unpredictable and you're not sure how long you need it. So I guess if you're first starting a company, you'd want to use on demand just because you don't know how much to spend. Right, okay. Next is reserved. You commit for a longer period, usually because usage is predictable. So this is best when you have a steady workload, long-term usage, and you know when to use it. Like signing a lease for a lower amount. Okay. So I guess this version is kind of like a monthly subscription where they charge you less, so you could go pay ahead. You could pay like $100 and you get like $200 worth of storage, or let's say 150 of storage. So this is much cheaper. Yeah. Yeah, see, you get your lower cost. So you do it cheaper, but you have a more steady. So you could run services, let's say your EC2. So you get a buying an EC2 is like the big computer, multiple servers. So with on demand, let's say you want two servers, you just pay for two servers. Well, for reserved, you'll just have this whole entire chunk reserved for you. And no matter what, you're gonna have to pay like let's say $20 a month for it, which is this like the bigger piece you get, the bigger you pay. Let's see. All right, next is Spot. Okay, next is Spot. Okay, so we covered on demand, which is the first one. Second one is going to be, um, what was it like renting? And now the third one's going to be Spot. Let's see. So we could use spare AWS capacity at a big discount. Cheapest option matters. Interruption is okay, and workload is flexible. Flying on standby on airline, cheap but not guaranteed. So I guess it's kind of like I'm gonna say this is kind of like an auction. So for example, you have your big computer again. The first one is you buy on demand. So you want that one. The big one, like you just rent it. And now Spot is like, okay, let's say this month Amazon was not able to use the full strength of their machine. They go ahead and just sell it for a cheaper price. So you're not guaranteed that in this month you'll have good that those spots will open up, but when they do, they're just gonna sell it to you for I guess for a really cheap price. So you should go ahead and recommend this service or this pricing option if you're fault tolerant, you're stateless, and you have a flexible start and stop. So basically for this, use Spot. So use Spot if you need cheap. If you need a super cheap option, you go ahead and go with Spots, and you can be interrupted. Interrupted prone, as in you're tolerant to it. Okay, let's go ahead and move to the next point. Okay, so reserved, that was the word. Yeah, reserved is kind of like renting. Okay, now we have auto scaling and load balancing. I briefly covered it, but now let's go dive deeper. So these are not extras, they are things that make EC2 usable at a scale, right? Because EC2 is usually, okay, oops, what's going on here? Okay, so EC2, Okay, so EC2 is basically, okay, let's think about it with the big picture again. So now that we have a good idea, let's just say this is Amazon, let's call it just AWS, right? So we have a little picture. It's divided into many virtual machines. I'm just gonna say this for this. I'll put this. This is us. So our server, let's go ahead and zoom in with that. So this is our server. This is our EC2. Our EC2 will be communicated to by other servers. So this is client. So our client puts a request. Oh, actually, our client will put a request on a load balancer, which is right here. And that load balancer puts it into your EC2. And your EC2 could actually just make other smaller services inside of it. So our EC2 contains EC2s. So we survey traffic spikes, stay available, avoid overload, and serve lots of users. Now we're going to learn about them one at a time. Let's see. So imagine our website runs on one server. At 2 a.m., the traffic is small. At 2 p.m., the traffic explodes. If we only had one server, let's say one server, which is, we could cross these out because we only have, actually, it's just, where's the erase button? Okay, so let's say we only had one server, because we do have one server right here. Let's say for this example, we're not actually going to use load balancer, so our client will just talk straight to our EC2. That'd be enough at night, but too weak during busy hours. Let's say many clients talk to this. So many clients, right? This thing will get overloaded and be laggy. Right. Number two is that it's not fault tolerant. Let's go ahead and scroll down more. Might be enough at night, but too weak during busy hours. What do? We could add more servers during busy times and reduce them when traffic falls. This is called auto scaling. So each one of these servers actually costs money, as we went over. So at 2 a.m., let's say 2 p.m., we need 4 servers, right? 4 servers. But at 2 a.m., we just need 1 server. So an auto-scaling group is a service which automatically launches or terminates EC2 instances based on rules. So we set a defined type of rules saying how many servers do I need right now. This is based on time. What if a server fails? So if a server fails, then you go ahead and launch new servers. What if traffic doubles? Then you want to launch more servers as well. And that's what auto-scaling group does. So ASG. So auto scaling group basically just scales the amount of servers you need based on a couple of conditions. So let's go ahead and do that. Scale based on conditions. Number 2, what do we scale? We scale servers. Or we could just say virtual machines, but also in our situation, because we're learning about Amazon, we call EC2. Right, so servers are known as virtual machines, and virtual machines are known as EC2, and EC2s are just virtual machines of the big server from Amazon. EC2, EC2, EC2. See, we could add instances and remove instances and replace unhealthy instances. So let me go ahead and draw this out for you. So let's say when the hour, let's say this hour 1, hour, say 12 a.m. we just need two servers, right? But when it switches to hour, let's say 2 a.m., we only just need one server. So we're able, what the auto scaling group, the ASG, can do is it could remove this server and just run one server just to keep costs low. So it just keeps costs low, right? Because why do we need so much computing power right here when no one's even using it? So we could scale out when demand rises. So also when the hour, let's say hour is 2 p.m., we could scale up. The auto scaling group could detect like, oh, okay, it's 2 p.m. now. We should actually add a bunch of servers just because our servers are being overloaded at 2 p.m. So we have to scale it out so that they're not overloaded. Seek improves cost efficiency and improves availability. So it saves us money. See examples, suppose your app is busy when CPU goes above 70%. You could tell AWS if CPU stays high, add more instances. If CPU drops, remove some. Yeah. Common scaling signals. Auto scaling can react to things like CPU usages, number of requests, queue length, and custom metrics. Okay. So number of requests are basically clients. CPU usage is how many instances are being used. Queue length is how many people are waiting in line from the load balancer. Okay, now we have to think about this exam-wise. How is this going to help us with the exam? So traffic is a variable, which basically means traffic is kind of like a number. So let's go ahead. So traffic is a variable. So let's say traffic is at like, let's say 90%. That's a variable. And demand changes over time. So sometimes it goes up to 90, sometimes it's 50%, sometimes it's 100%, which we don't want it to be 100 because that's not fault tolerant at all. And we need automatic scaling. So when it changes from 90 to 50 and 50 to 100, what's actually happening is the auto scaling group is scaling. Otherwise, if we did not have this, we'd have to either just run like 5 instances at all time, no matter how many people are using it, or we'd have to scale it ourselves. And it's not auto, just a scaling group, and you're the scaler. So what problem does a load balancer solve? So imagine you have 4 servers instead of 1. How does a user know which one to talk to? Okay, so let's see, auto scaling group scales based on demand. Based off the demand. Okay, now let's see, what does a load balancer solve? Now imagine you have 4 servers instead of 1. How does the user know which one to talk to? You do not want users choosing servers manually. All right, okay. Let me draw out that problem. So let's say you have like 100 customers. Let's say these are customers. I'm just gonna label them these circles. These people actually. Right? And then they want to use a service. Let's say we have 4 servers because our auto scaling group said 4. And then let's say every customer picks server 1. So I'm gonna say this is S1, server 1, server 2, server 3, server 4. Okay, so let's say they all pick server 1. You don't want that, do you? Because server 2, server 3, and server 4 are not being used at all, right? So when these servers aren't being used, you're just wasting money. What's the point of having low latency when they just have one server being overloaded, just ruining the latency, right? We don't want that. So that's why we have something called a load balancer. Go ahead and fix this up. That's why we have our humans, our clients, right? These people actually have to communicate something called a load balancer, right? Our auto scaling group, let's say pick 3 at this time, right? So instead of communicating directly to the server, right? Instead of these people talking directly to the server, which they could all just pick one, right? They talk to the load balancer first. And the load balancer says, hey, we don't want to overload S1, S2, and S3, right? So we should go ahead and just balance them out. It's in the name, load balancer. It's loading in the client into the server and it's balancing them out. So that's what load balancer solves. Load balancer could use different algorithms such as the round robin, or let's say first in, first out. So whichever customer came in first would have priority on which server they get to pick, or which server the load balancer picks. See, we don't want to choose them manually. We need something that receives incoming requests, decides where to send them, and avoids unhealthy servers. Spread work across many instances. See, that's where it balances out. I didn't go through the unhealthy requests. Let's do that. Okay, let's say we have a bunch of servers, 3 of them actually. Let's say one of them is unhealthy. Let's go ahead and just say this red one is unhealthy, right? If we had someone pick, if we had a client, right? They would be able to pick all of them, right? They could pick any. If they pick, if they chose to pick server 3, which is the red one, which is unhealthy, they would have a bad experience. And we don't want that, right? We want happy customers. So that's why we have a load balancer. So this load balancer right here would say, hey, look at this server. This server is not even good. Why would I pick it? So think about like a server, like a waiter. Before you walk into a restaurant, you talk to a waiter, and that waiter, let's say this is a waiter, he brings you to a table which is clean. Right, these are clean tables, and this is a table that someone just ate at and it's not ready. So that's what the load balancer does. Think of it like a server for a restaurant. It directs the traffic. Oh, okay, there's actually an example right here. Let's go ahead and read it. See, we could think of a receptionist. Think of a receptionist at a clinic. Patients arrive at the front desk. Receptionist sends each patient to the right available doctor. Okay, we could draw this out. These are doctors. Right? And then, oh, where'd it go? Alright, whatever. Whoa. Oh, this is disappearing ink. Okay. Okay, so each patient does not choose their doctor by just wandering in the halls, right? Because if they did, one doctor would be overloaded with requests and he wouldn't know who to help. And get unhappy patients. So we have a load balancer, which is like the front desk lady. It just distributes the traffic so that everyone has a better experience. So now that you've figured out that, let's go figure out the main reasons why we use a load balancer. So we use it because it's scalable. So that as our application grows and we have more clients, we're able to just direct the traffic so that no server gets overloaded. So also availability, as in that red one. If one is not there, then we could just send traffic to the server that does work. Simplicity, it hits one endpoint, not many servers. Yeah, okay. And health checks, does not send traffic to broken instances such as this one. Without a load balancer, traffic may go failed to a failed server such as this one. One server may get overloaded, just like doctors. If a doctor has many patients at the same time, that's not good. We want one doctor, one patient. After he's done, he can open up the availability again. And scaling becomes messy. So as more clients grow, we have a chance that they all might visit the same instance, which we do not want that. So now we have to learn about the different types of load balancers. We know what a load balancer is, but now we have to hit the subcategories. So the application load balancer, the ALB, is the most common. It's used for HTTP, HTTPS, web applications, APIs, path-based routing, and host-based routing. See what it means simply. It understands the web traffic. So I guess it's like request. So each client requests the application load balancer. And these are the applications which run on servers. So they can put in a request and they go. So think of this like web traffic. This right here is a web traffic. So you have to know this. So HTTPS is a request where your computer talks to someone else's computer, which someone else's computer is also known as a server. APIs is application interface. Okay, let's go on, move on to the next type of balancer. It makes smart decisions such as going to one service, API goes to another, and app company goes here. It understands application level request. Most modern apps are APIs, are web apps or APIs. So application load balancer shows up constantly. So an example is a company has a front end, an API back end, and a admin portal. Okay, let's go draw this out. So a company has okay, so this is company, right? And they have just a big part. This is their EC2. So their company has a front end. Let's just say this is front end. And this is the back end. And this is admin. So we have a client. Oh shit. Or whatever. We have a client. This client talks to the application load balancer. And they see, oh man, this request just says something. It wants to go to the front end. Let's say it's an HTTPS. So that goes to the front end. And they just go ahead and send the information back. So not only does it balance, it balances, okay, so front end has many servers, many front ends. Back end, let's say, has like 2 back ends. And admin has like 1 admin. So they go ahead and just, they verify the HTTPS, like, hey, this actually goes to the front end. Now from there, they pick which one of the front ends they want access to. And which one of the back ends they want to have access to. And which one of the admins they have access, based on the request that's given. So if a question says web app, HTTPS, URL paths, API, or website, you know it's going to be an application load balancer. Okay, let's try to map out these keywords. So web app. So web app, oops. Okay, so web app. It's kind of like, let's say, a website. HTTPS. You can see from like right here, like usually it's HTTPS, ChatGPT. You know, it's a website. URL. It's also like a URL, an API. It's like a request. Go ahead. So anything that points to the website is application load balancer. Next is a network load balancer. Let's go ahead and learn about this. Okay, so this is kind of like establishing connections. Network load balancer. So network load balancers are like establishing connections to TCP, UDP, very high performance and very low latency. Okay. So, network load balancer cares less about website paths and more about moving network traffic fast and efficiently. It's scary when it uses non-HTTP protocols. For example, if it did use HTTP, then we know that it's going to be the application load balancer. HTTP. The app is extremely performance sensitive, so I guess if you want really strong, so network load balance is performance sensitive. So let's say performance has to be quick. And the traffic is TCP or UDP, so establishing connections. Okay, let's go ahead and look at the example and see what they got. Void IP system using UDP, a game system using custom protocols, a very high throughput TCP app. These point more NLB than ALB. See how none of these actually mention using URLs or anything like that? So if the question says TCP, UDP, extreme performance, static IP, and low latency at a network level, we can say it's a network load balancer. Okay. Okay, so this one's less common, the GWLP. Let's see. This one is less common but very testable. It tests for application network appliances, firewalls, packet inspection, and third-party security appliances. Someone in traffic does not need to go to your app. Wait, let's see. What problem solves? Sometimes traffic does not just need to go to your app, but needs to be inspected first. For example, firewall checks, intrusion inspection, packet filtering, and security appliances from AWS Marketplace. GWLB helps send traffic through these inspection tools. Okay, let's see. Was there an analogy for this one? No analogy for this. Okay. Okay, let's go ahead and do a review. Oop. Okay. Gateway load balancer. Okay. So let's see. GWLP is gateway load balancer. And it kind of just uses security checks. So, okay, the first one was application load balancer, which is for like HTTP website. And network load balancer is like connecting, establish connections. So that kind of just establishes connections. It's like for UDP, low latency. And okay, so next is the GWLP gateway load balancer. So it's for firewalls, network appliances, packet inspection, third-party appliances. So it kind of uses to verify, inspect. So it could be firewall checks, intrusion inspection, packet filtering, and AWS Marketplace. So it kind of just helps send traffic through those inspection tools. So I guess we have a client, we have our GWLB, and we have different appliances. I guess one of them kind of just does firewall, one does packet packet filtering. When does security intrusion? So so they verify, let's see, categorize requests, and this sends them to one of these. And from there, it has many different versions of firewall checks. Remember that? Okay. So think of airport security. Before passengers reach the gate, they go through screening. So before a client goes through, let's say this is the gate. The GWLP system that routes traffic through that screening point. So this is say, hey, this is the security security guide. He says, hey, you're trying to go to Afghanistan, go over here. Hey, you're trying to go to USA, they have these regulations. These have these regulations. So exam shortcut. Okay, these are things that we have to know. So if an exam asks for a firewall application appliance, that's GWP, LB, traffic inspection, packet inspection, security appliance. So I would say security, safety. This points all to GWLB. Application load balancer points to websites. Network load balancer points to connection. Establish. Okay. Let's go ahead and check out the next ones. Why multiple area zones plus load balancer matters. So AZ, what does AZ stand for? It stands for availability zone. So if an availability zone is, okay, let's go ahead and draw this out. So in availability zone, let's say separate data. If we put all our availability zones in that, our servers in one availability zone, your app can go down usually from like a natural disaster. So pair this with a load balancer, because load balancers can send traffic to healthy instances, stop sending traffic to the failed zone if needed, and that's why the exam loves this pattern. High availability web app has multiple availability zones and load balancing and auto scaling. Okay. So let's say this is like USA and this is Canada. All right, so if this is two AZs. All right, this is AZ1 and this is AZ2. Right, so why do we need EC2 in USA and one in Canada? Let's say USA gets bombed by like Iran or something, right? So that means that this will actually not work anymore. So let's say if we only had one availability zone, then our service is down, our company is over because we don't provide any service. So why would someone go to our company? Well, if we had two availability zones, let's say Canada gets bombed or something, right? Then USA is still up. USA will still be good to go. So we are fault tolerant. Right, that's why we should have different availability zone. There's also other things like latency. Let's say if I'm from like USA and I send a request to Canada server, and Canada sends one back. This is much further, right, than if I just go USA. So it also depends on your location. Requests can be faster when you send your request to a server which is closer to you. That's why we should have multiple services. So now we have Lambda. Now we're switching mindsets completely. We're learning about the service which Amazon provides. So the first service we had was EC2, right? EC2 was our first one, which was Elastic Cloud Service, or cloud, I think compute, right? So basically it's just a virtual machine, which has, where we have to control everything, remember? We have to do a lot of custom stuff. Custom settings for like old stuff, old, outdated, right? Well, the new kid on the block is actually Lambda. We could just run code without managing servers, so we don't have to worry about load balancing. We don't have to learn about or worry about the network load balancer, or just protecting our things, right? Or protecting our servers, which is the GWLB. All of this, we don't have to worry about it anymore. Actually, we could just use Lambda. We don't have to think about servers at all. All we have to do is give our code, how it gets triggered, and what permissions it needs. AWS runs that for you. So that's why Lambda is called serverless, right? So basically all you have to do is, okay, so before, right? Before you, this is you, right? And you control a server, right? This is an EC2. EC2. And that EC2, you would have to have other EC2s in it. Let's say that. And you have like a load balancer, right? So go like that. You have to worry about all of this stuff. Right, with Lambda, all you have to do is just go like this. Instead of having that, all you have to do is provide code to Lambda, and Lambda will just give you back. That's it. You don't have to worry about all this other stuff inside here or anything. So it's serverless, right? So literally, it's not serverless to, like, there's no server at all. It's serverless from your point of view, because they have all of this into a box, and this box is labeled Lambda. So you don't have to worry about having all of that stuff. Just worry about your code, how it gets triggered, and the permissions it needs. See, serverless does not mean there's no servers. There are servers, you just don't have to manage them anymore. So you don't have to learn about scaling. You don't have to worry about scaling. You don't have to worry about provisioning or patching up, like fixing those broken instances. Right. For example, let's see. When a file is uploaded, just process it. When API requests, just run the logic. You don't even need a full server running 24/7. You just run code when it's needed. That's Lambda. So it has low operational overhead, which means operational overhead is kind of like operations that you have to do. So you have to do it to do, that's operations. So you don't have to worry about any of that. So it automatically scales. So it's like the auto scaling group. It just uses that, but you don't have to put the settings. It just knows. Pay only. So it's like pay by using an event-driven design, which basically means, let's say, if there's no servers, let's say no users equals no servers, right? And if there is like many users, then many users, many servers. It just does it all for you. So if the system says minimize management, event-driven, process on upload. So as soon as you upload, it starts processing. Serverless, unpredictable request pattern. Lambda is usually the best. Common Lambda use cases. Let's say a file lands in S3 and a Lambda gets triggered and resizes the image, parses the file, or transforms the data. So APIs, API gateway receives that request, invokes Lambda. That's the event-driven stuff. Event processing, so SQS, SNS, Event Bridge, and DynamoDB can trigger Lambda. Automation, so run small admin tasks automatically. What event-driven means? So example, an event could be a file is uploaded, a message is received, a timer reached 9 a.m. That's an event that happened. So it means that because something happened, we go ahead and run our code. So Lambda limits we should know. Lambda's great, but it's not for everything. A Lambda function cannot run forever. It has a max runtime of 15 minutes. So if the job is very long running, Lambda may not fit it. For an example, let's go ahead and actually just draw this out. So Lambda sounds like something like you just put it in and you don't have to worry about it, but actually it has limits, right? Let's say the execution time was more than 15 minutes. So if we have a file upload and that load takes more than 15 minutes, then we can't actually use Lambda. We'd have to use our EC2. Back to EC2. Use this instead. And let's see, stateless. So Lambda should not depend on memory sticking around between runs. So each execution should work like a fresh worker. So you should not depend on past information. So do not rely on local memory or long-term. Store in state Dynamo ET. Store state in S3. So not ideal for full server control. If you need custom OS, background, some other stuff, that's where the EC2. Remember, EC2 is like customizable. Okay. So if you need custom operating system access, background, daemons, all of that stuff. Okay, now we have to understand what a container is. Okay, let's go ahead and try to understand what containers are. So we're going to learn about ECS and Fargate. So what is a container? A container is a packaged application with everything it needs to run. So it's usually code, libraries, dependencies, runtime. The goal is run the app the same way everywhere. So another thing could be it works on my laptop, but not my server. Right, when you run into this problem, you use a container. Prevents this. So everyone has a different machine, right? So let's say I have like a MacBook and you have a Windows. We got to have it so that it runs on both MacBook and Windows. So containers kind of just, whoever created this, right? Whoever created the service will have all of their, they'll have all their code, their libraries, dependencies. So this is like code, all of that. So they would have this inside there and also their own system. So I'm going to say virtual machine details. Right, so we go ahead and put that on our EC2, and that's what a container is. So we contain it. So this is a container. So why do containers matter? They standardize deployment so that everyone could use your app, not just people with your similar machine. They could isolate apps, run microservices cleanly, and make scaling much easier. Okay, now we gotta learn about what is ECS. Okay, so ECS stands for Elastic Container Service. Right here. It's AWS service for running and managing containers. So you could tell ECS what container image to run. What container image to run, how many copies of it we should have, networking rules, system scaling settings. So ECS helps orchestrate containers. ECS with EC2. One option is to run ECS on EC2 instances. So an EC2 instance, let's just say this is an EC2. So you could run ECS on it. So we have ECS in it. Actually, ECS might be on the outside. No, we run ECS on EC2. Okay. So ECS is on your EC2. So that means your containers run on servers you manage. ECS manages those containers, but you still manage the EC2. So it's not fully hands-off. Let's see. Your containers run on servers you manage. Okay, so what is a container? This is, let's say we contain this. ECS manages those containers, so we manage that. Wait a minute. Okay, so your containers run on servers you manage. So these are servers. Okay. EC2 manages those containers. But you still manage EC2. So this is the whole EC2. And these are containers. Containers are in them. Okay, so each container is inside each of those servers. Okay. Fargate. Fargate is the easier container option. So ECS on Fargate. So you still use the containers, but AWS manages the server underneath. You do not provision the host. This is why Fargate is important. It gives you containers without server management. Okay. ECS on EC2. You rent a food truck and your kitchen inside it. Whoa. Okay. Okay, from this I'm seeing that EC2. So ECS is a type of container. Okay, it also has another container called Fargate. So EC2 on ECS on EC2. Okay. You rent a food truck. Okay, let's just say this is a food truck. Right, so you rent a food truck and you run your kitchen inside it. So you have a kitchen. It's our kitchen. We're in charge of this kitchen. Okay. You rent only the kitchen space and someone else handles the building and the infrastructure. So I guess what ECS, you have more control. So you focus on the app, not the host. Fargate is kind of, you just, there's a truck, but you don't even own the truck. You only own the kitchen. This is you. So when to use containers. So Fargate is like you're more focused on the server, and ECS is you get more control, I guess. Yeah, okay. hmm When to use containers. Containers are useful when your app is already Docker based. You have multiple microservices. You want consistency between development and production. You want more control than Lambda, but less work on raw EC2. When to use Fargate specifically? When the app is containerized, you want minimal engagement. You do not want to manage EC2 instances. You want scaling for containers without host ops. So the question says containerized app, Docker, microservices, minimized operational overhead. If the question says containers, but need control of the host, special host level software, managing underlying instances, EC2 on ECS, or ECS on EC2 makes more sense. Okay, let's go ahead and just try to map these out, memorize them. So Fargate leads to less control, less worry, right? Let's say when it's containerized app, Docker, so Docker just means is a container, which means it already has microservices, minimize operation overhead, so that's like less worry, microservices, containerized app. So we still need containers, but need control of those. So this is also a containerized app, but we need control of hosts. So I guess let's think of it more control. Special host level software, custom software. Manage underlying instances, manage instances. Okay. Okay. Let's compare and compute 4 choices in plain English. So EC2, you manage the server. Okay, so EC2, remember, like EC2 is like custom stuff. So when you need control, you have old software, very old stuff. It's the old way of doing it. More control. Okay, auto-scaling load balancer. These make EC2 scalable and highly available. So it just directs traffic. Kind of like a server, like actually a host, like in restaurants. We have different versions, such as application load balancer. We have a network load balancer and a GW load balancer. This is security. This one is for websites. And this is for connection. Non-HTTP. This is HTTP. Okay. Lambda, you just run code when needed. Okay. So Lambda is just basically everything we have, so just give it code. Lambda. I think it was like less than 15 minutes when it's low operations, short task, APIs and processing, containers and Fargate. Your package app cleanly, okay. Less than 15 minutes, serverless. Your package apps cleanly to AWS, so containers. Best one, you package apps cleanly and let AWS manage infrastructure. Best one, app is containerized, microservice. This is just Fargate. What was the other one? The other one was some sort of container. Let's see. Less flexible than Lambda. Oh, it was ECS. Okay. This whole category is important because almost every architecture starts the question, where should this workload run? And your answer changes everything based on cost, scaling, overhead, availability. If you choose one of the compute models, you may overbuild, pay too much, can create unnecessary admin work. Okay. Okay, so we want our own cloud server. So custom, like you want your own server. You want a VM, a virtual machine. Auto scaling. Yeah, add remove. Okay, add remove. That's pretty good. Load balancing. Auto scaling is like scaling, scales, instances. Scales, instances. Load balancer. That was the one where it's like a host direction. Lambda, give code, get output. Event driven. Containers, want to package my app cleanly. So that all VMs can use Fargate. I want containers without managing servers. So container without server. Okay. Let's see. So simple decision tree. Do I need full machine control? AWS. Yeah, okay. Yeah, okay, so custom. Remember custom. Full control. Yep, that's good. Is the web app with changing traffic? Is it a web with changing traffic? Okay, so we use auto scaling to manage each server, the amount of servers, and application load balancing to direct that. Is it triggered by an event or should have low operation? Lambda. Is it already containerized? Use Fargate. Is it containerized and want less management? Use Fargate. Is trafficking HTTP? Use that. Use ALB, which application load balancer. Is traffic TCP, UDP, or ultra high performance? NLB. Is it about security? Use this. GLWP. Okay. Common traps in each category. Okay. Make sure that we get the question right when it comes to exams. So when it says minimum over, oops. When it says minimal operation overhead, serverless, automatically scaling, event driven, yeah, this leads to Lambda. Because it's serverless, it's scaled automatically, event driven. Anything event driven will usually point to Lambda. Minimum operational overhead, that's also Lambda. Trap 2, forgetting EC2 usually needs scaling and balancing. Yeah, EC2 needs that because it's more customizable, right? Custom, so we get more power, more choices. So don't forget that it needs scaling and balancing. So this is application load balancing. Scaling is auto scaling. Choosing Lambda for long running. Nope. Lambda's good, but only for about 15 minutes. Choosing EC2 and EC2 Fargate is simpler. Yeah, this is only if you want more control. Right? If the app is containerized and they want less management, Fargate usually wins. Because you don't have to manage. See, Fargate does not need to manage servers, right? But these are all containers. ECS is Elastic Container Service. And this is also an Elastic Container Service for Fargate, but we don't actually have to manage the servers. So ALB is web traffic, NLB is network level traffic. See, kind of connections. Network, it's in the name, network load balancer. Web traffic, okay. So forgetting high availability means multiple AZs. Yeah, one instance in one availability zone is weak. To the USA, Canada example. Canada example. Okay, now this is a teach back version, so you guys could basically just a little quick reminder summary. So compute is part of AWS that gives your application a place to run. That's what computation is. EC2 is a cloud server you manage, it's a VM. Auto scaling adds and removes servers. Okay, we went over that. A load balancer sits in front and spreads traffic across servers. Yep. Lambda runs code without you having to manage any of the servers. Container package apps neatly. Fargate lets you run those containers without managing the underlying machines. So Fargate takes it one step further and you have less control, but less worry. Okay, now let's go ahead and go through examples. Solidify our knowledge. So a company has a normal website with lots of traffic. Okay, so a normal website with lots of traffic. Okay, a good fit is EC2 on auto scaling. Okay, you should also have ALB in front and multiple availability zones. Okay, why? Because it's scalable, it's highly available, and web traffic. Okay. Okay, I'm not even gonna look at the other part. Okay, let's see. I'm not gonna look at the answer, just go look at this. So resize uploaded images. A user uploads image to S3, a good fit. S3 event triggers Lambda. Why? Because it's event driven. So they uploaded an image, so you want to process it. It's a short task and no operation. Okay. Docker-based microservice. So it runs in Docker. Okay. So a complete company already has a container app, wants low operations, ECS on Fargate. So it's containerized, minimal. That UDP gaming service. A gaming service company needs very low latency and UDP support. Because it says very low latency, we first think of NLB. Example 5. So a company traffic inspections imply, I guess, GLLB, because inspection is kind of like security. And, see, firewall right here. By seeing firewall and inspection, you should think GWLP. Okay, now let's go ahead and do one last summary with the keywords. EC2, virtual machine. We have many control, auto scaling, scales the amount of servers we need. Server is also known as EC2. Load balancer is kind of just like a host which directs that traffic. ALB is a type of load balancer, which is for websites. And NLB is another one just for establishing connections using TCP or UDP. This one's for security. And Lambda is for a different code. Containers are packaged apps. So let's make sure that it runs on my machine. Whatever runs on my machine runs on yours. This is the same thing as a container, except it has less overhead, such as managing the underlying services, such as the servers. We don't have to manage them anymore. Yeah, see, containers without managing servers. And I think that is it. We covered everything for today. And that is the summary of computation when it comes to AWS. We went over all of this stuff. I hope you guys had fun, learned something new today. I know I definitely did. I love teaching, so I hope you guys learned something new, man. Later.